Welcome to Ask and Learn.
Okay, we have a problem with a problem for diesel engine cycle here, and we're given a compression ratio of 18.2, temperature at state 1 of 100 degrees Fahrenheit, which we convert to 580 Rankine, a pressure at state 1 of 14.7 psi absolute, and a temperature at the end of the heat addition process, which would be at 3, equal to 3200 Rankine. We're also told to assume constant specific heats at room temperature for air. So what that means is we can look at table A2E for constant specific heats at room temperature and write down the specific heats for constant volume, constant pressure, and of course the ratio of specific heats. So in the first part of the problem, probably leave those there a little bit for now, we are asked to find the compression ratio. So the compression ratio is equal to specific volume at 3 over specific volume at 2. But we're not given any volume, so we can actually use the ideal gas law for constant pressure process, because process 2.3 is a constant pressure process for the diesel cycle. And we can relate the ratio of V3 over V2 to the ratio of T3 over T2. So now all we have to do is find T2. And to do that, we can use an equation for the process 1,2, which is an isentropic process on a diesel cycle. So that means we can use the equation P2 over P1 is equal to V1 over V2 to the power of K, which is the ratio of specific heats. Interestingly, the ratio V1 over V2 is also equal to the compression ratio. So the compression ratio to the power K is equal to P2 over P1. And if we solve that for P2, we get 853.92 psi absolute. And then we use another isentropic relation here. T2 over T1 is equal to P2 over P1, all to the power of K minus 1 over K. Solve that for T2, and we get 1851.21 Rankine. And then we plug those temperatures into the equation for the cutoff ratio, and we get a cutoff ratio of 1.729. The next part, it asks for the heat rejection. So heat rejection, essentially we're just going to say is Q out, right? Which on a diesel cycle, heat rejection happens at process 4.1. That is the constant volume heat rejection. So we can use a simplified version of this equation where the heat minus the work is equal to the change in internal energy. And we're all assuming this is process 4.1, 4.1, and 4.1. Well, this is a constant volume process, so the work is 0. If you break down heat to heat in minus heat out at 4.1 is equal to change in internal energy, process 4.1. Well, there is no heat in. It's just not, there's no heat in it. This process, all we have is heat out because it's a heat rejection. So we're left with a negative Q out is equal to U1 minus U4. Oops, excuse me. U1 minus U4. There we go. Now to get rid of the negative, we just rearrange terms to get Q out is equal to U4 minus U1. Well, we need internal energies at states 4 and 1, but we're given the assumption of constant specific heats, which gives us this equation. The change in internal energy is equal to constant volume specific heat times the change in temperature. So we have Q out is equal to CV times T4 minus T1. And now what we have to do is we have to find T4 because we have T1. So to find T4, we're going to use table A17E with to find the relative specific volume at 4. But in order to do that, we need to first use some relations we're given. So if we have a cutoff ratio, which is equal to, was it V3 over V2, and our compression ratio of V1 over V2, we can rewrite those solving for V3 is equal to cutoff ratio times V2, and V1 is equal to the compression ratio times V2. So now we're going to use that in a relation here. We're going to say that the relative volume at 4 over the relative volume at 3 is equal to the volume at 4 over the volume at 3. What that's saying is these two ratios will be the same regardless of whether or not we have values for either of these. The ratios will equal each other. So then we can replace V4 and V3 on the right-hand side here with what we found up here. So V3 would be RC times V2. And V1, remember, we have a constant volume process, so that's the same as saying V4 is equal to R V2. So this is R V2, and we cancel out those, and we just have the compression ratio over the cutoff ratio. So then we can solve for the relative volume, specific volume is equal to the relative specific volume at 3 times the ratio of R over RC. And we end up getting 10.05. So now we look at table A17E and we find the relative volumes that are above and below that. And we get a low temperature of 1480 Rankine, a high temperature of 1520 Rankine, a low relative volume of 10.34, and the high relative volume of 8.578. So I'm saying here high and low. I'm just differentiating between the initial state and the state above it. So obviously relative volume at 0 is higher than relative volume at 1, but it's based off of these temperatures. So then we use the equation for linear interpolation that is solved for temperature at 4, which is equal to your initial plus your relative volume at 4 minus your relative volume at 0 times temperature at 1 minus temperature at 0 over relative volume at 1 minus relative volume at 0, and we get a temperature at state 4 of 1495.22 Rankine. We plug that into our equation. Q out is equal to our constant volume, T4 minus T1. We have everything we need here, and that is equal to 156.50 BTU per pound mass. So that's your heat rejected. The last part asks for the thermal efficiency. So thermal efficiency is equal to the network over heat added. network can be rewritten as heat in minus heat out. So then we have this equation to find thermal efficiency. Obviously we need heat in, but again, using the constant specific heats, we have this relation that heat in is equal to the change in enthalpy. The reason why I'm using this change in enthalpy is because at process 2-3, we have a constant pressure process. So we could use the constant pressure specific heat times the change in temperature at process 2-3, because that is equal to the change in enthalpy at 2-3. And fortunately, we have everything we need for that already. And we get a heat added of 323.71 BTU per pound mass, just per pound mass. Excuse me. And then you plug that into your thermal efficiency equation, and you get a thermal efficiency of 52.65%.